So this video is all about a different type of angle in circles called inscribed angles. Now we've already learned about central angles, which are angles that have a vertex at the center of the circle. An inscribed angle, on the other hand, has its vertex on the circle itself, and the two sides that make up the angle, and this is important, are chords of the circle. So in this case we have angle BDC being an inscribed angle because D is on the circle and BD and DC are both chords. Go ahead, pause the video, write this definition down, draw the diagram so you know what's going on, and then come back when you're ready to move on. So we're going to see a few different theorems and corollaries about inscribed angles, but the first thing we're going to see is something called the Inscribed Angle Theorem, which is that the measure of an inscribed angle is equal to half the measure of its intercepted arc. So in this case, our inscribed angle being angle BDC, its inscribed arc is the arc represented by BC, the minor arc BC, although it's possible for an inscribed angle to intercept a major arc too. So go ahead, pause the video, write this theorem down, come back when you're ready to move on. So this is true about any type of inscribed angle, that the measure of the angle itself is equal to half the measure of its intercepted arc. So we could look at a diagram like this, knowing that the angle BEC is 38 degrees, and we could calculate the arc BC and the angle BDC. So go ahead, pause the video, see what you can do on this based on the inscribed angle theorem. Come back when you are ready to see the answers and move on. So the inscribed angle theorem tells us that the measure of this arc BC is twice as large as the measure of the inscribed angle that intercepts it. So the angle is 38 degrees, which means the arc is 2 times that, or 76 degrees, because that is 2 times 38. Now we can find the measure of angle BDC because its intercepted arc is also BC, and so we divide that by 2 to get back to 38 degrees as the measure of angle BDC. And so angle BEC and angle BDC, both being inscribed angles, intercept the same arc and have the same measure. And that is something that is a corollary to this inscribed angle theorem, which is that two inscribed angles that intercept the same arc are congruent. And therefore, any angle that intercepts the same arc as any other inscribed angle is congruent. All inscribed angles intercepting this arc BC are congruent everywhere on the circle. So go ahead, pause the video, write down this corollary, come back when you're ready to move on to the next one. So what this allows us to do, this corollary to the inscribed angle theorem, allows us to find the measures of angles in lots of places on a circle, just knowing that they intercept the same arc as inscribed angles. That also means, and we'll see this in class, that there's a particular relationship between the central angle and the inscribed angle that both intercept the same arc. Another corollary of the inscribed angle theorem is that if you have a semicircle and the inscribed angle intercepts the semicircle as its arc, that angle is then right. So in this case, we have angle BEC, and because arc EC is a semicircle, that means angle EBC is a right angle. Go ahead, pause the video, write this corollary down, including the diagram, so you can see what I mean. Come back when you're ready to move on. And so this actually creates an interesting idea as it relates to circles anyway. That means this point B can float anywhere between E and C over here. So we could put this point, we'll call it B prime, and draw that inscribed angle that intercepts E and C, and it is also a right angle. And that's just something unique about inscribed angles that intercept semicircles or whose endpoints create a diameter. So now we're going to move on to some other angles that can be created here. Based on what we saw from tangent lines and radii, where tangent lines and radii are 180 degrees, we can also say, and this is true, that the measure of an angle formed by a chord and a tangent is equal to half the measure of the intercepted angle. And so if we have the diameter EC here, which we know is perpendicular to the line going through C, well, the intercepted angle is this full 180 degree semicircle between C and E, which means that the measure of angle EC, let's call it D here, at 90 degrees is half the measure of that intercepted angle. Similarly, over on the right-hand side of this diagram here, where we have E not being in a place where we can create the diameter, if the arc CE is 72 degrees, that means the angle created here, again we'll call it BCD, must be 36 degrees, or half of that intercepted arc. And the intercept, or the intercepted arc, let's actually fix that. That should say arc and not angle. So go ahead, pause the video, write down this property of chords and tangent lines, come back when you're ready to do a few practice problems, and move on. Okay, so I'm going to give you 2 slides of problems to do that just give you a chance to work with the ideas that we just saw. Here are the first 2 problems. You're going to solve for the missing values in each of those problems. Come back when you are ready to see the answers and move on to the last problem. So in the diagram to the left, we have a whole bunch of inscribed angles that all intercept the same arc, which means all of those angles by that first corollary to the theorem, to the inscribed angle theorem, are all the same. So x and y both are 19 degrees because they intercept the same arc as the 19-degree angle, and that arc there is 38 degrees. In the diagram on the right, this is a series of chords that intercept a semicircle at a diameter. So this angle over here is a right angle. Angle x is an inscribed angle that intercepts an arc that is 46 degrees, so x is 23 degrees. And finally, angle y, we can do this in a bunch of different ways. We can find the remaining piece of the semicircle and take half its measure to find angle y, or we could use complementary angles because x and y together must add up to 90 degrees, which means that y is a 67-degree angle, or if you calculate it the other way, that this is a 134-degree arc. One last problem for you to look at. Here's a quadrilateral that is drawn inside a circle. There's not a whole lot of related inscribed angles here, but see if you can find inscribed angles that don't intercept the same arc, but intercept arcs in a way that will allow you to use the entirety of the circle to calculate it. So go ahead, pause the video, write down this, or pause the video, calculate these values, and come back when you're ready to see the answers and end the video. So being able to calculate these angles requires recognizing that some of these inscribed angles don't intercept the same arc, but they intercept opposite pieces of the circle. So this inscribed angle, creating a 91-degree angle, intercepts this entire blue arc here. So that blue arc has a measure of 182 degrees, which means the remaining arc around it has a measure of 360 minus 182 degrees, or 178 degrees. That arc is intercepted by the angle that we are calling x, and together the 91-degree angle and the x-degree angle intercept the entire circle. Half of 178, because that's how we calculate the size of an inscribed angle, is 89 degrees. And so we can observe that 89 and 91 degrees are supplementary angles. Similarly, the angle formed by 115 degrees here intercepts an arc that is twice that large, or 230 degrees. The angle that is created by y intercepts the rest of the circle because the endpoints are the same. The rest of that circle is 130 degrees, which means that the measure of angle y is 65 degrees. And again, we notice that 65 degrees and 115 degrees are supplementary. And that is just a property of quadrilaterals inscribed into a circle, as their opposite angles are going to be supplementary because the inscribed angles that are created by those angles intercept the opposite pieces of the circle. So a few things that we saw in this video. One is that the inscribed angle theorem, the measure of an inscribed angle is equal to half the measure of its intercepted arc. We saw that 2 inscribed angles that intercept the same arc are congruent, and we also saw a few things related to angles that are created by chords and tangents that follow the same rules as inscribed angles.